This is example 6.4. And again, we're using law of conservation of energy to determine how fast an arrow shoots from a bow. Our before and after situation, our initial, you can see here, is when the bow's just before it's released, and then the final is just after, not letting the arrow go very far before we call that the final. And here, again, we're going to argue that energy is conserved and no work is being done by air resistance or, for instance, wiggling the string afterwards, which is kind of a bad assumption, but we're going to go with it. So here we're going to use conservation of energy, the generic formula again, and I'm going to write it all out, and then we'll cancel terms as we go. So we have initial kinetic plus gravitational to begin with, plus elastic potential, plus work equals final kinetic, final potential, final spring, oops, and then any change in internal energy. Okay. So to begin with, nothing's moving, and all that energy is stored up in the stretching of that bowstring, which is like a spring. Sorry. Okay. Now, we don't have any information about how high this bow is off the ground. But looking at the picture, it looks like we're going to assume that the arrow is not going to drop by much, and neither is the bow. So, we could set our reference level or our origin for the y direction is going to be right here. Okay. And although we know that the arrow would fall because of gravity, we're using such a short interval of time here that we're going to assume that either no work is done by gravity or that really no potential energy change is occurring here. Okay, so no kinetic to begin with. Potential energy, if we just set our origin right there, we also have none. Okay, but we do have spring energy stored up initially. And so remember the formula for that is 1/2 times the spring constant times the amount of stretch squared, which we have, which is great. And then we're assuming no external forces acting on the system during this short time period. Okay, and then kinetic energy final, of course the arrow is going to move and we want to know how fast. So here we're putting our kinetic energy formula in. But then these last terms, okay, the gravitational potential, spring potential, and change in internal energy, we're going to assume those are all 0. So all of these right here, those are going to be 0. So then this becomes a real simple problem. Mass does not cancel this time because we don't see it in the equation for elastic potential energy. So we do need to know the mass, but they did tell us what the mass of the arrow is. Okay, so then we have 1/2 the spring constant, and we have our stretch amount and set that equal to the mass of the arrow. And we can solve for final velocity. When we talk about what our system is, right, I do think it's worth saying that the system is the arrow and the bow together, right? But in the beginning on the left side here, we're putting in the stretch of, this spring constant, right, goes with the bowstring. So that's energy stored in the bowstring, okay, but the bowstring is touching the arrow and is going to force that forward. Um, there's no stretchiness in the arrow itself, right? And then because a person is holding the bow is not going to move, just the arrow is going to move. So we're not including the velocity or the mass, sorry, of the bow itself in here. But we could, I mean, we certainly could add a term over here, 1/2 times the mass of the bow times its velocity, but that's going to be 0. So what we're trying to do is, what the archer is trying to do is take as much of that elastic potential energy and get it in the form of kinetic energy of the arrow alone. Okay. All right. Oops. So then when we solve for this, now we're just plugging and chugging. The half appears on both sides, so you could just ignore that. Multiply both sides by 2 and be done with that. So I get 144 here. Newton meters, which is a joule, right? And then I've got 0.09 and when I finally take the square root, then I get a nice round number of 40 meters per second for the arrow. Pretty quick. Okay.